Okay, in this video, I will be discussing my reviewer on metallurgy. Actually, it says here module 11, but it's actually 10. I'll have to change that later. Um, but yes, this is the first lesson of the fourth long exam for chemistry for engineers. And okay, yeah, let's start already. So we have the most abundant metals on Earth's crust. So that's basically aluminum, sodium, potassium, calcium, magnesium. I believe this is titanium and manganese. I haven't really gone through the transition metals uh, that much yet compared to the non-metals. Yeah, so it's not so familiar to me. Okay, so sodium, calcium, and magnesium are sourced also from seawater, and calcium and magnesium in particular can be found in corals that are located in the seabeds. So, okay, manganese nodules, um, they are a source of magnesium, iron, nickel, cobalt, and copper. Okay, um, so in metallurgy, there are various processes that we have to know. I believe the first thing is the phase where we prepare the ore. So, after obtaining the ores from various sources, ores, by the way, are desired because they have a high concentration of the metal of interest. Um, so, we start preparing them. There are various ways to do it. We have flotation, magnetism, and amalgamation. Um, okay, minerals can also be used, but metal extraction. Okay, we'll get to that later. First, let's talk about flotation. So, in flotation, collected ores have to be separated from dirt. So, just remember the key word dirt. That's already flotation. When you separate clay and silicate materials, basically they are called gangue. You separate them from the ore. Since clay and silicate materials are hydrophobic, um, you can separate them using hydrophobic and hydrophilic substances in the flotation device. So there's this word called frothing. So yeah, the flotation device froths them out. Okay. So earlier, what I mentioned was ores. This is more desired in comparison to minerals, for the purpose or whenever we want to um, extract precious or desired metals from them. Um, since ores have a higher concentration of the metal of interest in comparison to mineral counterparts, minerals also contain concentrations of desired metals, but you have to know that metal extraction processes are expensive and at the same time they're time consuming. It doesn't take a short while to carry out these processes successfully. So in consideration of those factors, you prefer using ores instead. So okay, wait, back to first page. So yeah, if you want high yield, um, if you want to extract a lot of desired metals reasonably, you would choose ores. Minerals generally have a lower yield of metal of interest. So that's basically it. So next is magnetism, another process in the preparation of the ore. So some minerals, especially the ones that contain iron, are magnetic. So with this property in mind, they can be separated from a gangue. Again, a gangue is called, it's another term for clay and silicate materials. So you separate them using a magnet. So that's basically it. Magnetism. Okay. Amalgamation. So this is a process where one metal will dissolve or combine with another. So for example, mercury or Hg can amalgamate gold, usually small pieces of gold. When gold is in larger pieces, well, that's a different process. It's associated with a different process. But yeah, if it is in small amounts, amalgamation would be the appropriate process. So yeah, you have to know also that mercury is the main source of toxicity in gold mining. So since most metals are found in compounds are bound to anions such that metals are positively charged. The resulting charge can be their oxidation numbers. Okay? And okay. So after discussing the three processes in the preparation of the ore, let's move to the next phase, which is the production of metals. So we have how many? Three in this page. Okay, so basically three in this reviewer. So we have roasting, chemical reduction, and electrolytic reduction. Where do we start? Um, so okay, let's start with roasting. So this is a two-step process. So volatile impurities are removed and you convert your compound to a more reducible form. Okay. Okay. Metals can have positive oxidation numbers. Therefore, they can be separated from their combined forms through the reduction process. So, yeah, not all compounds are reducible though. Um, so, you have to undergo a preliminary process first to convert the ore to a more reducible chemical state. So, in a way, roasting plays an important role in making this possible because the goal is we want the compound to be in a state that's to be in a state of appropriate reducibility. So, in a way, you can say roasting is a preliminary process. So, yeah. Another way of um, metal production is chemical reduction. So, you use a more electropositive metal. This electropositive metal, by the word electropositive, meaning more negative standard reduction potential, which is abbreviated by E degrees. So, you use a more electropositive metal than your target metal, or in other words, desired metal, to more easily perform a chemical reduction process and isolate the target metal. So, the the more positive your standard reduction potential is, the more it wants to be reduced. The more negative it is, on the contrary, usually this is associated with group 1 metals. They have this property uh, in common. Well, basically, the more it wants to be oxidized. Because again, group 1 metals, well, they are called alkali metals. So, yeah. So, the more electropositive metal has a more negative E degrees. So, it wants to be oxidized. For example, here, We have magnesium. Here we have aluminum. Both of them have a negative standard reduction potential. I believe these are in group 1. Um, no, not necessarily group 1. Aluminum is in group 3. Magnesium is in group 2. But technically, they're still metals. So yeah, maybe it is certain that this property is not just limited as a characteristic of just group 1 metals. So here, I'm not sure what this is called, but this is the one that wants to be reduced, as well as this. So a more electropositive metal, that's magnesium and aluminum. Electropositive, by the way, is essentially the opposite of electronegative. So I believe, if I recall correctly, the most electronegative element is fluorine. And the trend is, if you go up, in the periodic table, if you go up and you go to the right, so go northeast basically. And you might ask why noble gases aren't considered, therefore, if the trend is supposed to be upwards and to the right. They're noble gases. They're an exception to electronegativity. Therefore, the group at their left, the halogen group, to where fluorine is. So essentially, fluorine is the most electronegative because it's located at the topmost of that group. I think period 2, group, the second last group from the right. Okay? So, yeah, electropositive has a more negative standard reduction potential. The third process is electrolytic reduction. So, essentially, if chemical reduction cannot be done, which is usually described as when you want to isolate very electropositive metals such as sodium, you don't have to find a more electropositive metal anymore, which is what you usually do in chemical reduction. So you usually carry this out on the anhydrous molten oxide or halide of the metal. Then from there, you forcibly extract the target metal. I'll need to consult more on this. It's not easy to understand by just reading. Okay. So there are metals. Metals are essentially in the form of either mineral or alloy. I think this is supposed to be the first page. Anyways. So a mineral is a naturally occurring substance with a range of chemical compositions. So most metals are made out of minerals. So a substance basically means two or more elements. For an ore is described as a mineral deposit that is concentrated enough to allow economic recovery of desired metal. So this is what you usually select when you want to extract or isolate a metal, because it has a higher yield for a target metal. So if you've played Minecraft before, it's not easy. It's not hard to understand what an ore means. It contains your iron, your copper, your emerald, your gold, your diamond, your coal. But it has to go through a combustion process first before you can get them. That idea applies for some of them, if not all. Anyways, for alloy, this is a solid solution, either of two or more metals or of a metal or metals, with 1 to more nonmetals. Okay, so let me just repeat what I just said in a more simplified manner. It may look confusing at first, but okay, so there are combinations um, that an alloy can be composed of. So, two or more metals, one metal, sorry, two to more metals, or of, okay, that is kind of confusing. Two or more metals, or of a metal, or metals with one to more nonmetals. So essentially, a combination of metals or a combination of metals and nonmetals at the same time. So, yeah. So, if ever your target metal um, is a nonmetal and it is combined with other metals or nonmetals, this portion they're not considered impurities. This one is. Okay, so what is the study of metallurgy? Or basically, what is metallurgy? It is the science and technology of separating metals from their ores and of compounding alloys. So, to recover a metal from its ore, three phases, two of them which we already discussed: prepare the ore, produce the metal, and the third one is to purify it. More on that later. So, we have various primary types of minerals. We have uncombined carbonates, halides, oxides, phosphates, silicates, sulfides, and sulfates. So some ores, though, are almost already pure. So, for example, we have pure gold, pure silver. So yeah, that kind of sort. So yeah. So these primary types, the types that I've mentioned, they are categorized according to bounded anion. So it has something to do with the one that's written in green. So halides combined, usually a combination with bromine, chlorine, fluorine. So they're all negative. Carbonates, carbonate, sorry, phosphates, oxides, sulfides. What the heck? Yeah, so sulfides, sulfates. Okay. Let me just check the next page where phase 3 is. Okay, I think this part is still considered under metal production. So this is a more specific case. So in the case of producing iron, um, we can use a blast furnace. This technically is considered a reduction process. So the iron ore is introduced into a furnace along with limestone and coke, not the soft drink. Okay, this this word also has its own meaning in the context of earth science. So a blast of hot air is introduced into the furnace. This hot air contains oxygen. This reacts with the carbon in the coke. Therefore, the carbon monoxide and carbon dioxide are produced. Carbon monoxide here is considered the main product. Carbon dioxide is just considered a byproduct. So, yeah. Stainless steel is mostly iron, right? And iron is found in the Earth's crust in abundance. We have various kinds that are found inside the Earth's crust: iron pyrite, iron carbonate, hematite, magnetite. So these in particular contain more iron atoms compared to these two. But essentially, iron is extracted through blast furnace. So yeah, going back to the idea that carbon monoxide is the main product, it can react with the iron compounds at different temperatures. So at lower temperatures, um, well, there's a span from 200 degrees Celsius to 2000. Um, okay, I'll get back to this later. Actually, let's continue for a little more. So, three key steps to extract iron using a blast furnace are described in the three highlighted reactions. So, yeah, carbon monoxide can react with the iron compounds at different temperatures. So, I believe this is iron oxide. When you react it with carbon monoxide, you produce extra CO2, and this one goes here. You react it with carbon monoxide again, and you produce FeO and CO2. CO2 will always be a byproduct. FeO plus CO at around 700 degrees Celsius, so it would produce iron. This is where iron is finally extracted. Carbon dioxide, on the other hand, is a byproduct. It combines further with the carbon in coke in order to produce more carbon monoxide for extraction process. So as you might have already figured, um, it's it implies a cycle. So carbon monoxide will always be produced as long as the cycle keeps going. So at 1200 degrees Celsius, iron starts to melt and molten slag forms. Contrary to what you may think, the process doesn't stop here at the part where iron is finally extracted. You have to see molten slag forming, and at around 2000 degrees Celsius, two carbons plus an oxygen will produce two carbon monoxides. Okay. Limestone, what was mentioned earlier, contains something called calcium. I believe this is carbonate. So when you roast or heat it, it forms calcium oxide. I think that's what you call it. And this reacts with the impurities found in the ore. So yeah, impurities: silicon dioxide and aluminum oxide. What's produced are part of the molten slag. So molten impurities, if you want to, what does it say? So these are molten impurities that you want to separate from the molten iron. So you collect the molten iron at the bottom of the furnace. The science behind this is the molten iron's density is greater than that of the molten slag. So in that sense, you can collect molten iron from below at the very bottom, the slag somewhere above. So iron collected this way still contains a lot of impurities, so you call it pig iron or cast iron. This one is a more familiar term. It has a very low melting point and can be cast to different shapes and forms. So yes, to separate impurities, you do this. A blast furnace has to be designed such that it would be able to separate molten steel from molten slag. More on this in the next video.